Section 14.2, Buffered Solutions. This is sometimes a either challenging chapter or a very easy subsection of the chapter for people. My caution to you is that just because you've gotten this tool that we're going to use in a second, do not treat everything as a buffer problem. Not all acid-base problems are going to be buffer problems. What we're going to see is this Henderson-Hasselbalch equation. It's incredibly useful, but just because you got a hammer, don't go around making everything into a nail. All right, a buffer solution. And guys, I've come across buffer solutions. At some point in your life, you are actually a living example of a buffer solution. Your blood is buffered to a particular pH, a physiological pH. So it can absorb acids and bases produced by biological reactions without changing your pH. So if you're outside of that physiological pH, you can enter acidosis or alkalosis. Those are very serious medical conditions that are fatal. It may contain a weak acid and its salt, or a weak base and its salt. Really, a buffer is going to be when you have significant amounts of a conjugate weak acid and its conjugate weak base. It doesn't matter whether it's coming from the weak acid and its salt, or a weak base and its corresponding salt, or you added in a weak base and a weak acid together, or you took some weak acid and you added in some strong base and converted that into its conjugate weak base, or you started off with a weak base and you added in a little bit of acid to make the conjugate weak acid. As long as you have significant amounts of a conjugate acid and its corresponding conjugate base, you have a buffer, right? And this buffer solutions are just solutions of weak acids or bases that contain a common ion. That's why it's got to have that conjugate in there. And pH calculations on buffer solutions require the same procedures used on other solutions. So we can go through and do a ice table with a little bit of stoichiometry and say, well, here's this common ion just like we did for the HF and F minus. That solution where they had HF and sodium fluoride in solution together, that is a buffer. Yep. The pH calculations for those, we can do them just like we did with any ice table before. All right, so step one, don't freak out just because you hear the word buffers. We're going to treat it, we can treat it just like we do any weak acid with a common ion or weak base with a common ion. Right? Set up an ice table. We're going to see that there's an easier way to do this. So, and then we've got this idea that when a strong acid or a base is added to a buffered solution, we're going to deal with the stoichiometry of the resulting reaction first. So the characteristic of a buffer is that it's able to resist changes in pH upon addition of strong acid or strong base. So we're going to do this if we have to stress our buffer. This is called stressing our buffer. When we're going to do that, we're just going to do a stoichiometry step first and see how the calculations are going to be completed. We're going to subtract some of our weak acid and convert it into weak base. Or if we're adding in a strong base, we'll convert some of our acid form into the conjugate weak base form. Right? It's not too bad. And I will show you an easier way in class on how to deal with a stressed buffer, okay? So pay attention for when that worksheet comes out. We'll go over that in class, and I'll show you the easier way to do this. Right? So here's the problem-solving algorithm, right? We're going to start with an original buffered solution. We're going to add some H plus or OH minus, and we're going to get a modified pH. Step one is we're going to do some stoichiometry calculations to figure out our new concentrations of conjugate acid and conjugate base. Step two, and then we're going to do an ice table. So then we'll figure out the modified pH. So we've got to break this down into two steps. One where we're doing stoichiometry, consuming some of our weak acid or weak base, and then we're going to throw that into a new modified ice table. So let's look at an example. A buffered solution contains 0.5 molar acetic acid, and we're given the Ka, and 0.5 molar sodium acetate. We're going to calculate the pH of that solution. This is the initial buffer pH. And when we get to Henderson-Hasselbalch, we're going to see that there's an easier way to do this. All right, so the major species in solution are the weak acid, the sodium, which is not going to affect the pH at all, the acetate, which is the conjugate weak base of the acetic acid, and then some water. And that water is not going to contribute significantly to the OH minus concentration or the H plus concentration. An examination of the solution components shows that the acetic acid dissociation equilibrium, which involves both acetic acid and acetate, will control the pH of the solution. Now, some of you might be wondering, could I do this and use a KB? Yes, you could, right? You could easily set this up and say, well, I'm going to consider this conjugate base the primary component. I'm going to do a KB instead, and I'm going to have my OH minus, and I'll have the up here where the H plus is, and I'll have the acetic acid here, and I'll have the acetate down at the bottom. But why do that? It's going to come out the same way whether we look at things from the acids perspective or from the bases perspective. So just stick with the acids perspective because you're usually going to get this Ka. It's a lot easier to think of if you're being consistent. Right. So our initial concentrations of each of these are as follows. So we've got 0.5 molar of our acetic acid and acetate and no H plus. We're going to lose some acetic acid. We're going to generate some acetate, and we're going to generate some protons. Our corresponding ice table is set up like this. We've got our balanced chemical equation on top. We're starting off with 0.5 molar of each of our conjugate weak acid, conjugate weak base, and we've got 0 molar H plus. We're going to lose a little bit of our acid to form some H plus and the conjugate weak base, giving us our equilibrium concentrations. We're able to plug that back into our equilibrium expression. We've got a numerical value for K. We've got our products over our reactants. We'll have X times 0.5 minus X over 0.5 minus X. And so we'll make that simplifying assumption that X is small. So we'll have X times 0.5 over 0.5. So X is going to be 1.8 times 10 to the minus 5. So our H plus concentration is X, which is 1.8 times 10 to the minus 5, and our pH is 4.74. Suppose a buffered solution contains relatively large quantities of weak acid HA and its conjugate base A minus. When hydroxide ions are added to that solution, since the weak acid represents the best source of protons, we're going to undergo this stoichiometry step. Right, so this is when we're going to stress our buffer. We're going to add in a strong base. That hydroxide is going to react with our weak acid to form the conjugate weak base and water. The net result is that our hydroxide ions are not allowed to accumulate. They don't build up. It's not going to stay as a strong acid, but they're going to be replaced by more of our weak conjugate base ions. So if you add in some hydroxide, right, you're going to expect that that pH is going to go up. And what we're going to see is it will, because now our ratio of conjugate weak acid to conjugate weak base is skewing a little bit more towards the base side. So we're going to expect our solution to be a little bit more basic. So we're going to take our original buffer pH. We're going to add some OH minus to it. And we're going to find the pH of our buffer is going to be close, but a little bit more basic. So our added hydroxide ions are going to be replaced by A minus ions. And you're going to lose some of those HA ions as well. The stability of pH under these conditions can be understood by examining the equilibrium expressions for the dissociation of HA. So our Ka is going to be H plus times A minus over HA, or we can rearrange this to get H plus is equal to Ka times the ratio of HA over A minus. In other words, the equilibrium concentration of H plus, and thus the pH, is going to be determined by the ratio of our conjugate weak acid to our conjugate weak base. Right? When we add OH ions, the HA is converted into A minus, so our original pH is going to be controlled by this ratio of HA and A minus. We're going to add some hydroxide. We're going to lose a little bit. This concentration is going to go down, and this concentration is going to go up. The amounts of HA and A minus originally present are very, very large compared to the amount of OH. And then the change in HA ratio is going to be small. It's still going to change, but it's going to be a small change. And so our pH, which is controlled by that ratio, shouldn't change very much. The essence of buffering is that our HA and A minus are large compared to the amount of hydroxide that we added. So when our strong base hydroxide is added, the concentrations of HA and A minus change, but only in very small amounts. And under these conditions, the ratio of conjugate weak acid to conjugate weak base, and thus the H plus concentration, are going to remain very steady. Right? So if we look at this graphically, right, we're starting off with a ratio of HA to A minus. And if I add a little bit of H plus, I'm going to gain some weak acid, and I'm going to lose some of my conjugate weak base. If I add some hydroxide, my concentration of A minus, my conjugate weak base, will go up, and my concentration of HA will go down, but not a lot. Right? So it is going to get a little bit more acidic if you add, pH is going to drop a little bit if you add in some strong acid. The pH is going to go up a little bit. It's going to get a little bit more basic if you add in some strong base, but not by very much. So this brings us to the Henderson-Hasselbalch equation. Now this is where I'm warning you about not using everything as a hammer. Just because you've got this cool little tool here, right, does not mean that every problem is going to be a Henderson-Hasselbalch buffer problem. Right? You have to have a buffer. You have to have a conjugate weak acid, conjugate weak base in significant amounts. You cannot add so much of strong acid or strong base that you break the buffer, right? It's still got to have, like I said, significant amounts of both of those things. But when we reduce it and we take the log of both of our sides, so remember we had that H plus is going to be Ka times that ratio. Well, let's do the minus base 10 log version of that, and we're going to say that our pH is going to be equal to our pKa plus the log of AHA, the element of surprise. So it's going to be the log of the conjugate base over the conjugate acid. For a particular buffering system, conjugate acid-base pair, all the solutions are going to have that same ratio, that are going to have that same pH. So there is a base form of this, looking at things from the base's perspective, where it's like pH is equal to like pKb plus the log of HA over A minus, and maybe be a POH, but don't use that one. Just memorize this one. Work with this one, right? This is the one you want. This is important, right? It's going to make life easy if you know it, and the way to remember it is the log of AHA, the element of surprise. And I'm going to show you how to work this guy in class when we stress the buffer. So let's do an example. The pH of a buffered solution. Calculate the pH of a solution that contains 0.75 molar lactic acid, and they've given us a Ka, and 0.75 molar sodium lactate. So lactic acid is a common constituent of biological systems. It's the buildup of lactic and pyruvic acids that makes your muscles burn. That's one of the things I was actually working with the DoD and oh gosh, it's some horribly complicated military acronym, but it's like the Modern War Fighter Project, and they wanted to measure lactate buildup in people who were in combat situations so they could measure the stress that they were under physically for their muscles. And so that's one of the things that I worked on building a sensor for. So example, it's found in milk and is present in human muscle tissue during exertion. Our major species of in solution are going to be our lactic acid, right? Our sodium, which is not going to affect the pH, our water, which is just our medium, and then our lactate. Since the sodium has no acid-base properties and water is weak acid or weak base, the pH is going to be controlled by the lactic acid dissociation. So we're going to get our Ka is going to be products of reactants, and we're given a numerical value for that. Since our concentrations of the acid and the base are relatively large, right, we're going to say that it's going to be about the same at equilibrium for both of those as the initial concentrations. Thus, using our rearranged K expression, we're going to have our H plus is going to be Ka times the ratio of the weak acid over the weak base. And we end up with a value of H plus as being 4.2 times 10 to the minus 4. And our pH is going to be minus log of that, or 3.38. Right? Let's do this the easy way with Henderson-Hasselbalch. So this involved getting out an ice table, thinking about what's going on. We plug it into Henderson-Hasselbalch, right? We're going to say pH is equal to pKa plus the log of AHA. We took our pKa value just by doing minus the log of the Ka. Gives us 3.85. And then our log of the ratio of the conjugate acid to the conjugate base over the conjugate acid, and we end up with 3.38. So you can think of this Henderson-Hasselbalch equation as kind of being set in the middle, where you've got a pH equals pKa. And if your concentration of HA is equal to your concentration of A minus, your conjugate acid and your conjugate base are both the same, like let's say they're 0.25 molar and this guy's 0.25 molar, then pH is going to be equal to pKa. So your pH is going to shift a little bit to the acidic side if that ratio changes. So if you've got a little bit more on the denominator, right, your HA goes up relative to your A minus, you're going to shift it a little bit to the left, and you're going to get a lower pH. It's going to be a little bit more acidic. If your A minus concentration is a little bit higher, right, than your HA, you're going to shift it in the positive direction, over to the right. You're going to be more basic. So it's saying, I'm going to take this value here, and then I'm going to adjust it in a loggy kind of way based on this ratio. And it's going to be positive if I've got more base. And it's going to be a negative adjustment if I've got more acid. So let's do another example. We've got a buffered solution containing 0.25 molar ammonia with a Kb of 1.8 times 10 to the minus 5 and 0.4 molar ammonium NH4Cl. Calculate the pH of this solution. Our major species in solution are going to be the ammonia, the ammonium, Cl minus, which is not going to affect our pH, and H2O. So our dominant equilibrium expression here is going to be that the ammonia, which is going to be a weak base, is going to generate a weak acid and hydroxide. We've got our Kb expression. So if they give you a Kb, go ahead and do it from the basis point of view. If they gave you a ammonium, Ka, just go ahead and do it from the acids point of view. So our Kb is going to be NH4 plus times OH minus is going to give us NH3. On the bottom is our reactants. We'll set up that ice table where we got our 0.25 and our 0.40. We're going to lose a little bit of our base, form a little bit of our acid and our hydroxide. So we get 0.25 minus X, 0.4 plus X, and X. We're going to assume that X is small. So we say Kb is going to be our products over our reactants. We're going to plug in the specific values. We're going to assume X is small. And now we're going to get this ratio, 0.4 over 0.25 times X is equal to Kb. We're going to solve for X, and we get 1.1 times 10 to the minus 5. That's our hydroxide ion concentration. Our hydroxide ion concentration was 1.1 times 10 to the minus 5. Our pOH is going to be 4.95. Subtracting from 14, we get a pH of 9.4, which is basic, which is where we would expect it to be. This case is typical of a buffered solution in that the initial equilibrium concentrations of the buffering materials are essentially the same. There's not been a big change to those concentrations. Buffers contain relatively large concentrations of a weak acid and the corresponding weak base. They can involve the weak acid HA and the conjugate base A minus, or a weak base and the conjugate acid BH plus. So when I add H plus to a buffered solution, it's going to react. It's going to go essentially into completion. It's going to take our conjugate base and reform some of our conjugate acid, or it's just going to attach to that weak base and form its conjugate acid. When OH is minus as added to a buffered solution, it's going to react essentially to completion with the weak acid present. So our OH minus is going to react with our weak acid to form the conjugate weak base. Or you could say that our hydroxide is going to react with the conjugate acid and form the conjugate base. The pH in the buffered solution is determined by the ratio, again, of the concentrations of the weak acid and the weak base. As long as that ratio remains virtually constant, the pH will remain virtually constant as well. This will be the case as long as the concentrations of the buffering materials, the HA and A minus, are large compared to the amount of H plus and OH minus added. This is what we're going to call buffering capacity.